Section 4.5. Let's run another problem. Let's do another fence, but we'll modify it a little bit. And we're going to change a little bit what we're asking. We're going to sort of change the restrictions and what we're asking for. So kind of pre-wrote it out, the rectangular fence along the side of a building. So we'll kind of keep that the same, but it has an extra divider to create two equal-sized rectangles. My drawing, my building came out all kind of crooked. So we'll sort of try and straighten that out just a little bit. But I mean, in theory, this is what we're looking at. So you've got sort of, a rectangular fence again, and you have this sort of extra divider. So whatever your sort of width is, in the last one, that was our sort of width was X, and then our length, the other dimension we had is Y. So what's happening now is instead of just like two X's, we have a third X sort of running through the center, right? So if we need a total area of 120 square feet, what are the dimensions that will minimize the amount of fencing needed? So we've modified a little bit the setup, and we've also modified what we are asking for, right? And so we've kind of flipped the role of which is the like primary function that we're trying to sort of maximize, or in this case, minimize. So let's write that function out, I suppose, first things first. So we want to minimize what's kind of like, it's not quite the full perimeter, right? We're trying to minimize the materials, right? So maybe this is like materials M would be, 3 lengths X plus 1 length Y, right? 3 X's plus 1 Y. So that's the length of the fencing that we need, or use F for fencing. It doesn't particularly matter, right? So what's our restriction? Well, the restriction here is the area right, needs to be a certain size. So we need to fence in 120 square feet. So the restriction is our area, which would be X times Y. So that needs to be 120, right? So same basic strategy. We're going to use the restriction. We're going to sort of rearrange that, solve it for one of these variables. X or Y. Let's do Y, I suppose, because the Y is sort of by itself here. So in this case, this would mean, right, that like the Y by itself would be 120 divided by X, right? Or you could think of that as 120 times X to the minus 1. So if we sort of replace that and use that in our sort of materials equation, our main primary equation, sort of M, becomes 3x plus y becomes 3x plus, right? Y is now 120, x to the minus 1. So I needed that equation, my sort of fencing equation, that function in one variable. What's the domain, you ask? So it's interesting, right? Now, the domain usually comes from just like the practical limitations of the restriction equation. In the last setup we did, right, the domain was essentially based on having 80 feet of fence to work with. And so that meant we, in that case, we worked with X values from 0 to 40 because there were always going to be two pieces that were length X. And so they could only be as big as 40 each to get the full 80. This is different, right? So the area is 120. Area is kind of funny because, it's a value you get when you're multiplying the length and the width, what would be our X and our Y value. You can make that length, that X length, very, very small, but you can never make it 0 because if one of the dimensions is 0, then the area is 0. And of course, what we want is that the area to be 120. So the restrictions on X, right? So X will be on, essentially it will start at 0, but it's going to be an open interval because we can't actually hit 0, right? In this case, if we're trying to multiply to 120, X can be very, very tiny, and then that sort of in turn gives us potentially a very, very big Y value, something that will probably obviously be impractical. But like technically it's an option. And so the limit there would be, okay, the X could really be like microscopic, and we could sort of still get to 120 square feet if we just have a gigantic Y. So it's going to be an open interval starting at 0. And then the other side, right, if we sort of think of this from the other dimension, well, the X could essentially be as long as you want, and then you would just sort of counterbalance it with a very small Y value. So in this case, you know, if your restriction equation is this sort of like product, you know, product that has to hit a number, X could essentially be any positive value. So the interval here is going to be anywhere from 0 to infinity, you know, open intervals. That will affect a little bit how we kind of determine if we have a minimum. We'll have to use sort of specifically like a first derivative test rather than the 4-1 where we're like checking it at the endpoints, because the endpoints in this case just like don't exist as far as like a closed interval. So we'll come back to that. We just sort of need to like notice it. So we're essentially trying to minimize. So 3 times x plus 120x to the -1 over the interval 0 to infinity. That's what we're working with. So let's do some calculus. Let's take a derivative. So m prime, right? 3x goes to 3 plus, I guess it will be sort of negative 1 times 120 x to the -2. That sort of came out kind of funny, right? So this essentially is 3 minus 120 over x squared. Right, we're going to have to find critical numbers, so we should start to rewrite this. Then if we sort of say, well, this would need to be sort of common denominators, this becomes, if this is x squared and x squared, this becomes 3x squared minus 120 all over x squared. So that's our derivative. Regular stuff will look critical numbers, right? So we need, you know, bottom equal to 0. That's going to happen at x equals 0. That's essentially outside of our domain, right? So we kind of said we can't have one of the dimensions actually be 0 because, you know, it would give us, we wouldn't hit the 120. We could also see in the original function, I mean, this sort of in terms of x, 3x plus 120 over x, I mean, we can't divide by 0 here anyway, right? So there's a number of reasons where the 0 is really not going to work. So the only critical number we're really going to get, it looks like, is from 3x squared minus 120, right? So that's the top, equal to 0. Quick little rearrange, 3x squared equals 120. So then that would mean that x squared is 120 divided by 3 is 40. So x is, you know, the positive or negative root of 40. Another one, you know, the negative here doesn't really make sense. This is a length. This is an actual like real world length value. It wouldn't be negative. So we'll just use the positive here. We'll kind of acknowledge it, but we don't need it. You know, simplified, you know, this doesn't root all the way down. You know, we could write this, we could condense it to, you know, 2 times the root of 10, right? 4 times 10 is 40. The root of 4 is 2. That's a positive number. That's certainly in our interval. What we'll do instead of comparing the intervals is we'll do essentially just like a first derivative test. So let's consider, so anything from 0 to infinity, right? So this is 2 times root 10. That's essentially, right, the square root of 40. So let's test, right, m prime, and then we'll sort of see our m values above it. So what's less than the root of 40? Well, certainly something like 1 is less than that, right? Because 1 squared is 1. And so that sort of relationship would hold. So if we test m prime at x equals 1, where's our prime, right, is 3x squared minus 120 over x squared. So that's like 3 times 1 squared minus 120 over 1 squared. that's pretty clearly going to be negative, right? So that's negative over positive is negative. That's good news, because what we were hoping to find is a minimum. And so that tells us that our graph, our function, right, our sort of materials are decreasing, dropping from 0 to this like 2 root 10. What about something that's bigger than that? So what is this, square root of 40? So if I did the square root of 49, that would be 7. Or if I did the square root of 100, would be 10. There's lots of numbers that we could use that are bigger than that. Let's do 10, just regular 10, I suppose. So m prime at x equals 10, 3 times 10 squared minus 120 over 10 squared. That's 300 minus 120 over 100 is positive over positive is positive. So this is behaving in the way that we were hoping. And, what we can kind of see here, right, is that like essentially over the whole domain of this function, we're really only doing two things. We're decreasing to this point, and then we're increasing from that point onwards. That's enough to tell us that over this interval, that's not just a relative minimum, but that's an absolute minimum, right? To have anything else be smaller than that, you would need to be decreasing again at some point. We're just not doing that. We would have seen a critical point. We would have had other information that told us that was an option. So that tells us that we're going to have our minimum at x equals 2 root 10 in feet. The y that goes with it is what, right? We go way, way, way back, kind of up to the top. X times y is 120. So y is 120 over x. If I carry this around, make sure I'm still in frame. So my y dimension, 120 over x, 120 divide by 2 root 10. This is going to have to be rationalized. So this becomes essentially 120 root 10 over 2 times 10. So 120 root 10 over 20, this becomes 6 root 10. 6 root 10 feet. Obviously, if you were actually making this fence, you would need to, turn those into decimal numbers, right? To be able to sort of cut and measure them and go from there. You can kind of see the relationship here between them, and you could almost maybe take that and generalize it a little bit, that it looks like in this case where there are sort of 3 different x's for every one, where are we, right? 3 different x's for every one y. What we ended up with here is a y value that's 3 times as long as the x value. I'll sort of leave it up to you to determine and do the math that would say whether that is always true in this situation or not. So anyway, that's another setup. I'm going to do, I think, 2 more where I'm just going to talk through the setups. I'm not going to sort of fully solve them. And that will be in the next video or videos, not in this one. This one is over. Goodbye.